This video is about analyzing circuits. So let's start off with a problem. We're asked to calculate the total resistance of this circuit here. So this circuit here has a 10 voltage power source. This little squiggly line actually indicates that it's an alternating current power source or voltage source. It doesn't really matter for our calculations, just a word of interest. So this circuit has three resistors. Resistor 1 has a resistance of 100 ohms, resistor 2 500 ohms, and resistor 3 400 ohms. So if we're asked to calculate the total resistance of the circuit, this is a circuit in series, right? All the resistors are just one after the other. So if we assume that the voltage source doesn't have a resistance, these are just the only three resistances, all we have to do to calculate the total resistance of the circuit, so I'm going to call it RT, is just the sum of those resistances. So it's going to be 100 ohms plus 500 ohms plus 400 ohms, which gives us a total of, not very much space here, but it gives us a total of 1,000 ohms. Okay, so that's good. That's the total resistance of our circuit. So essentially, if we wanted to sort of simplify this diagram, really what we have is a circuit that looks like this, with our 10 volt potential difference source, and then we have one resistor there that's equivalent to 1,000 ohms. These two circuits, this one here and this one here, are basically the same in terms of talking about resistance in the whole circuit. So we can replace these three resistors with one resistor that's 1,000 ohms. So when we do that, we can easily calculate the current through the circuit, because all we have to do is use Ohm's law. Ohm's law states that resistance is voltage over current, right? Or if we want to solve for current, we could just rearrange that or swap that R and that I to give us that current is equal to voltage over resistance. So in this circuit, we know the voltage is 10 volts, right? Or the electric potential difference is 10 volts, because that's what the source, the voltage source, provides. So it's just going to be 10 volts over a total of, and we know that we calculated the resistance, the total resistance, so I'm going to put actually total resistance here. The total resistance is 1,000 ohms. And if we do that, we're going to get 0.01 amps. Or, if you see in the answer here, I converted it to milliamps. So I just divided by 1,000 to get it into milliamps. Either way, it's same thing. Now the next question is, how much voltage does this circuit lose through each resistor? Because we know the whole circuit adds up to 10 volts, right? But some of that voltage is lost across each resistor. The total should add up to 10, but we can calculate what it loses across each resistor, right? So now that we know that the circuit, we don't actually know the direction that the electrons are going to flow in the circuit, but let's pretend they flow this way, right? Let's pretend they flow around here, around here, around here. Notice how it's one loop, it's one continuous loop. So we can assume that there's 0.01 amps everywhere, right? That doesn't change. That part can't change because you don't lose any electrons as it goes around the circuit. We're going to assume they're all there. So basically the current going through each one of those resistors, right, is 0.01 amps. So in order to calculate the voltage drop for each resistor, we again can use Ohm's law. This time we're going to solve for voltage though. So in Ohm's law, we can solve for voltage. It's just going to be I times R, right? So if we look at resistor 1 has a resistance of 100 ohms, right? It's the one up here. So if we're going to find the voltage in that, or the voltage drop for that resistor, it's just going to be I, which is the current, which we know is 0.01 amps everywhere, times the resistance. And the resistance of that resistor by itself is 100 ohms, right? If we do that, the voltage drop for that resistor is going to be, if we multiply that, it's going to give us 1 volt. So that's it. Across resistor 1, that is going to lose 1 volt. If we do the same thing for resistor 2, right, we can just multiply again the current, 0.01, times the resistance. And the resistance of that resistor is 500 ohms. So it's just going to be times 500, which gives us a voltage of 5 volts. So 5 volts of electric potential difference are lost here, 1 volt is lost here. So if the total's got to be 10, right, because that's what the power source provides, you should be able to figure out what this is without even calculating it, right? Because it's got to lose, the amount that it loses here has got to be the same that it gains here. So if it's 5 and 1 for these other two, you should be able to figure out that it's going to be 4 for this one, because those three have to add up to 10. But let's calculate it anyways. I know we're sort of running out of room here, but we can just sort of do it underneath. For resistor 3, the voltage is going to be 0.01 amps times 400 ohms. And that's going to give us 4 volts, exactly what we predicted, right? So essentially what's going to happen, I'll do this in red so it's a little bit clearer. We're going to gain 10 volts from our battery, or from our power source, I should say. We're going to lose 4 volts here. We're going to lose 5 volts here, and we're going to lose 1 volt here. And if we add those all up, so it's going to gain 10, lose 4, lose 5, lose 1, it sort of comes out to 0 in the end. All those cancel out. And that's what we want. That's a way of checking to see if it works out. And that's exactly what we're doing here in question D. It says check your answer for C by adding up the voltage across the 3 resistors. What does the voltage law say? Well, it says basically that the total voltage in the circuit has to be 0, or the total number of losses due to resistors have to be equal to the total number of gains. So we can usually just show that math as, so the voltage, the total voltage is just equal to 10 volts, which is positive because it's from the source, minus 4 volts, minus 5 volts, minus 1 volt, which is 0, which is what we want to see, right? And 10 volts there is just the total voltage of the circuit, the total voltage gain of the circuit. Okay, here we have question 2. A little bit of a different type of circuit because the resistors here are connected in parallel, right? So what's going to happen to that electricity as it flows, or the electrons as it flows through the circuit? We know the electrons like to go from negative to positive. So what's going to happen is the electrons are going to flow this way. And then at this point here, they're going to split up. Some of the electrons are going to go this way. Some of them are going to go this way. And so that means some of them are going to go through this resistor and some of them are going to go through this resistor. And then they're going to come back together over here and go back to the battery. So there's basically 2 paths that the electrons can follow. They split here, and then they come back together here to go back to the battery. So that's why this might be a little bit more tricky, but you'll see it's similar to the previous question we did. First of all, we need to calculate the total resistance of the circuit. So in order to do that, I'm actually going to label these resistors. I'm going to label this 35 ohm one, resistor 1, and I'm going to label this one here, resistor 2, just so we can keep track of what's going on. Our formula for resistors in series, or parallel I should say, is 1 over the total resistance equals 1 over resistor 1 plus 1 over resistance 2, right? So if we just plug in R1 and R2, we should be able to solve for RT, or our total, right? So 1 over RT is going to equal 1 over, well, our resistance 1 is 35 ohms, plus 1 over resistance 2, which is 15 ohms. Now this is the part where you can just use your calculator basically to figure this out. So I'm going to do 1 divided by 35 plus 1 divided by 15. What that gives me is it gives me a very small number, 0.09 blah, 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 blah. So that's going to give me 0.09523 to, I'm going to say 9524. So the thing to remember here, I'm actually going to continue this over here. So that means 1 over RT, the total resistance, is equal to this number 0.09524, blah, 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 blah. So in order to find our total resistance, we need to flip this fraction here. And in order to flip this fraction here, we need to flip this thing. So the easiest way to do that, if this number is already in your calculator, all you have to do is 1 divided by this number. So I'm going to do in my calculator 1 divided by the previous answer. And that tells me what the total resistance is. So in this case, the total resistance, when I do 1 divided by this number, 1 divided by a fraction just flips it. It gives me 10.5 ohms. So the total resistance of this circuit is 10.5 ohms. And that makes sense because it makes sense that the total resistance is less than the two other resistances, because it's actually easier when the electron path splits up, because only some of the electrons are going to go through here, some of the electrons are going to go through here. So it's like you're making it easier for the electrons to go through the resistors because there's less electrons going through, right? Each one. So it makes sense that the total resistance is actually less than that. So if we were to redraw this circuit with just that one resistor, so let's redraw this circuit really quick, and it's like we replaced those two resistors in parallel with one resistor that's 10.5 ohms, right? That's essentially what we did. We reduced this confusing looking diagram to a much simpler one, right? Oh, also we know this is a 9 volt, maybe a 9 volt battery that's hooked up to it. Yeah, it does say battery, so that's a battery. So there we go. So can we find, now that we've reduced it to one simple resistor, we know the total resistance, can we find the current? Very similar to that previous question, right? If we glance up at the previous question, we just found the total current by using Ohm's law. I equals V over the total resistance, right? So we're going to do the same thing here. I is just equal V over the total resistance, right? The voltage we know is 9 volts, and the resistance was 10.5 ohms. If we do that, 9 divided by that gives us 0.871, blah, 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 blah. Or sorry, 0.8571. So it does round to two significant figures to 0.86 amps, which is the same as the answer that's listed there, or 860 milliamps, either way. So that's how much goes through the whole circuit. That's not bad, right? So we know basically how much circulates around this whole circuit here, and that's 0.86 amps. Now the next question is, how much of that goes through this resistor, resistor 2? How much of that goes through resistor 1? When this splits up, how much of it goes here, how much of it goes here? So that's a little bit maybe more of a difficult question, because we have to sort of look at each of these resistances separately. You might think it's complicated. It's actually not that bad. We just need to look at each resistor separately. So if we look at resistor 1 by itself first, resistor 1, think about this. What's the electric potential difference across this resistor? Well, because we don't really think about wires very much as having a change in resistance, they don't have any resistance, right? In this case, we're assuming they have no resistance. So this battery is a 9 volt battery. So the difference, the electric potential difference across this resistor is actually just 9 volts, right? Because think about it, this part here, nothing is changing, and this part here, nothing is changing. So the voltage across this is 9 volts. Same thing with this one. So the voltage across each one of these is just 9 volts. So if we know that the voltage drop is just 9 volts across each one of these, we can use Ohm's law to calculate the current, right? Because we know that the current, I, equals V over R. So for resistor 1, we're saying the voltage drop is 9 volts, and the resistance, well, we know it's 35 ohms. It says 35 ohms in the question, right? So if we do 9 divided by 35, it gives us a current of 9 divided by 35, sorry, I did that wrong, 0.26, about 0.26 amps. Now let's think about it. Does it make sense? Well, it does. It's a smaller number than this one, right? And that makes sense because some of the current is going to go this way and some of the current is going to go this way. So that number looks like it's going to be okay. Let's check resistor 2. I equals V over R. And in this case, voltage is still 9 volts. But the resistance is 15, because it's given in the question as 15 ohms. 15 ohms. If we do that math, 9 divided by 15, that gives us 0.6, exactly 0.6 amps. I know we're sort of going into this next question here, but the answer is 0.6 amps. So it's basically telling us if we zoom into this diagram here, it's basically telling us 0.26 amps of the current is going upwards to this resistor here, and 0.6 amps is going to this resistor here. Now, does this make sense? What was our total current here? Think about that. What was our current here that was coming from this side? Well, we calculated the total current in the circuit was 0.86 amps, right? So this would be 0.86 amps. Does that make sense? Well, think about it this way. If we divided up 0.86, will the 0.6 and the 0.26 add up? They do. If you add 0.26 and 0.6, it's going to add up to 0.86. So this 0.86 was just divided up like that. Same thing on this side. When the two currents come together, the 0.26 and the 0.6, they're going to add back up to a current of 0.86 amps. So it makes sense. Our math checks out if you sort of follow this logic. And that's what the next question is asking us for. It's asking us, check our work for B and C by adding the currents through the resistors. What does Kirchhoff's current law say about the values for B compared to C? And that's exactly what it says. It says in any place where there's a split, the currents coming out of that split have to equal the current going into that split, right? So it makes sense because 0.86 is equal to 0.26 plus 0.6. So that would be sort of this junction here, right? And the same thing happens here where we have the two currents coming together. 0.26 plus 0.6 come together to make 0.86. These should all be amps, by the way. So both cases sort of check out that, that we did the rest of the math right. Okay, so you can always check your work by checking Kirchhoff's laws, either for voltage or current.